All right, class, welcome to lecture number 11 of CIVE 360. Recall that we are looking at now the problem of torsion. This is the second loading that we're putting on a relatively simple solid. The first was the axial. And for axial, remember, we have the two common expressions of sigma is force divided by area. So the resulting normal stress is basically a constant. And then as long as everything is uniform, if the load, the cross-sectional area, and the modulus elasticity are constant, we have delta is PL over AE. So by axial, that means that we typically have a one-dimensional solid like this, and we're just either pulling or pushing. And it's remarkable, actually, how many structural systems have that sort of behavior. But, and we've gone through some of them, we'll go through a lot more, and during your career, you'll go through and you'll see a lot more of these. But the second one, so that was number one. The second one is the torsion, and in that case, we're taking that, it could be the same solid, and we're twisting it. So I'm gonna put the double arrow notation. Now again, the double arrow, that is the right-hand rule. You use your thumb points in that direction. And then you rotate, you twist the solid in that particular direction. So we use single arrow for force, double arrow for a moment, and in this case it is moment about the long axis. And remember then that torsion is the type of deformation. It wouldn't be necessarily wrong to use the word twist, but whenever we say twist, we typically think about theta, which is going to be the angle of twist. And that is actually the displacement that we care about. So if we've got a particular section like so, and a straight line was originally like this, and it moves this way, that's typically the theta that we care about. So again, we would be twisting it in this particular direction. So it starts from the dashed line and it ends up there. And so you've got to be a little bit careful about the words that you use. So remember, torsion is linked with a type of deformation, and that is there's an opening up of the angle. It was here, now it's here. So it's no longer at 90 degrees, and that is basically then the shear strain. And that shear strain leads to a shear stress that balances that applied torque. And the reason we study this second is because the axial is driven by purely a normal stress and a normal strain. Torsion, I'm going to abbreviate it here, is driven by a pure shear stress and a pure shear strain. So it's kind of nice because in the one problem, we only have one type of stress, and now in the second one, we only have another. And what have we found so far? Well, we have our memorized formulas that look like this. The shear stress is actually linear over the radius. So it's equal to the torque times the radius divided by J, the polar moment of inertia. So that is the applied torque. And again, you do not want to switch the words torque and torsion. Torque is actually the applied moment that's going along the axis. The rho we're using as the radial distance from the center of our circular section. And then J is the polar moment of inertia. And again, we want to commit to that one to memory. So that is equal to pi over 32 times, if it's hollow, d outer to the fourth minus d inner to the fourth. If it's solid, then di is equal to 0 for the solid case. And you just get pi over 32 times the diameter to the fourth power. Remember that we use diameter rather than radii because common stock sections are typically called out by their diameter, not by their radius. So those are the two formulas that we have committed to memory. I'll kind of draw a box around that one, and then our J formula as well. You've got to have those in the back of your head. You don't want to be looking those up during a job interview or even on the job. That would be totally embarrassing. So the visual that we've got then, as we draw this, if this is the end face, we've drawn this last time, and even if it's hollow, so let's draw a second one like this, then the stress is going to be a straight line. So we draw in a linearly increasing intensity, and we draw the arrows like this. So they would be on this face, but they would be tangential. So it would be a shear type of stress, and that is going to be our maximum. The maximum shear stress for a homogeneous, solid, or hollow is always going to be at the outermost radius, because it's T rho over J, and that's where we hit the max. Now, normally what we would do is we would immediately do a numerical example, but we're going to actually wait on that so we can kind of kill two birds with one stone. So before we move on and show an example, let's talk about the displacement. Let's talk about the angle of twist. Because that is a big deal. If you're designing a section for torsion and you're applying a torque to it, you want to know how much the rotation, how much that theta angle is going to be. Let me redraw it. We just did it upstairs. But we're saying if it was originally here and it ends up here, then how much is that angle relative to, say, some fixed basis? So if we fix that end and apply the torque at this end, then how much angle of twist are we going to get? Well, what we do in this case is go back to our kinematic model. And incidentally, this is kind of typical for a solid mechanics analysis. Remember, we go from displacement to strain to stress to force. In this problem for torsion, it looks like this. If I apply a torque, it twists theta. That theta leads to a shear strain. That shear strain leads to a shear stress. That shear stress gives a moment or a torque that balances the applied load. So what we did was we started with this and we moved that way, and we made that connection, and we found that tau is equal to T rho over J. But now what we can do is we can take that result and then move. We can now go this way to get an expression for theta. Not theta factorial, I'm just being excited. So we have that expression in order for us to be able to kind of come back and close the loop on what the angle of twist is going to be. So remember what we did. We focused on this arc length. So if we had this length, that is our L, then we had two ways of finding out what that arc length was going to be. So I'm going to go ahead and write recall, because this was from our former class. It's from our former derivation. We had that arc length at the outermost fiber would be C times theta would be equal to gamma at C multiplied by L. That would be at the outermost edge of the cylinder. But then we also made that interior cylinder inside, and we had that rho times theta was equal to the shear strain at any radius multiplied by the length. So we actually derived those just by using our basic kinematic model about the nature of the deformation. And remember, the nature of that deformation was basically that everything moves like a straight line. Moves as a straight line. It's the Occam's razor model of deformation. In other words, picture how this thing can deform and the easiest possible explanation and go with that. And it turns out to be correct. Well, let's focus on this one, because now we can make the link. So I have rho times theta is equal to gamma at rho times L. Now, when we did the derivation, we didn't know what this was. We didn't know what the shear strain at any arbitrary radius was. But now what we can do is we can use the shear stress to get that. So I can write that that would be the tau at any rho divided by G. So that would be the shear strain multiplied by the length. But now we have the tau at any rho. So the tau at any rho is actually what we've just been shortening to tau, because it's implied that that's going to be at any radial distance. So that's going to be the torque multiplied by that radial distance, all divided by J. So we dropped the rho just because we decided, hey, we don't really need that rho. We are going to assume that it's going to be calculated at any one of those arbitrary radii points. So this is going to be T rho over J, that's tau at rho, and then the G comes here. And then we've got I'll put that in parentheses, times L. and that is going to be equal to rho times theta. So notice what happens. The rho's cancel, and we are left with theta is TL over JG. Big, big formula for us. So clearly we want to memorize this one. Now here's a helper. Remember what delta was? Delta is PL over AE. Theta, TL over JG. You see what I'm saying? They rhyme. Who says engineers don't do poetry? Actually, I say that, but I'm not a big fan of poetry. But in any event, those formulas rhyme, so PL over AE, TL over JG, so it's easy to memorize. And notice what it tells us. We've got the torque upstairs, so the forcing function is upstairs just like the axial force was upstairs. It accumulates over the length, just like the axial stretch accumulates over the length. The bigger the cross-sectional property, so the larger the second moment of the area, the smaller the twist, just like a cross-sectional property of the area. And then we've got a material property downstairs, a material property downstairs. So there is a very, very tight analog with axial. And again, that is based on the fact that these are very simple deformations. And so those relatively simple deformations then are going to lead us to relatively simple formulas. So now, since we're ending about our time space for this first lecture, now we've got tau is equal to T rho over J. We have the angle of twist is TL over JG. And then we also have J is pi over 32, D outer to the fourth minus D inner to the fourth. So those, at this point in our study of torsion, are the formulas that we want to commit to memory. And we are done with part A.